Hi, sorry about that. This is going to have to be the second video. The rubber band snapped. So what I was saying was, when you are writing these, the way these are written, you will always have the name of it followed by a dash, and then what its atomic mass is. So this is potassium 37, this is iron 53. Okay, so what happens in this particular decay? Potassium is going to lose a positron. So this is a positron. And what is a positron? Here it is. And here's its charge. So it's a 0. It's basically an electron that has a positive charge. So it's a 0 and then a positive 1. So let's look at the homework. So it just told me that's a 0 and a positive 1 electron, but this is actually called a positron. So what would this be? That would be a 37, because 37 and 0 is 37. And let's look up potassium. Potassium is, I believe, 19. 19 is correct. So it's potassium 19. So if that's 19 and that's a positive 1, this must have to be 18, because 18 and 1 is 19. So what's 18? 18 up there is going to be argon. Argon. Okay? All right. Hopefully you did pretty well with those. The bottom is the same as the top. For tonight's homework, this is in your little packet that I gave you. It says nuclear decay on the top, and I want you to do the front. Okay, the first page. I don't know if they're front, back, but I want you to do up through strontium 38. Okay? And this one, it tells you these are alpha particle emissions, this group is beta decay, and this one is positron. So you're just not as much using that chart. Okay? All right, so we're looking at positron emissions, separation of emanation, and nuclear equations today. So far, just to recap, we've done alpha, we've learned alpha, which is the very first one, beta, which are essentially high-speed electrons with a negative charge, gamma, which is not a particle, it's basically energy, has good penetrating power, can cause some damage. And today we'll be learning about positrons. Oh, I feel like I already did that, but if this is a repeat, it's okay. Okay. Positrons. Positrons, and this is true of all of them, we start with an unstable nucleus, and in this case it emits something called a positron. Positron is a similar mass to an electron, but with a different charge. Now, sometimes you'll see the word magnitude that goes with that. That positive one is its magnitude, a negative one would be the magnitude of an electron. So essentially a positron is an electron with a positive charge. Okay? And you can also think of this kind of like a beta emission, because beta emission is an electron, okay? And it's sometimes shown as a beta plus, and as I showed you before, it's also shown like an electron with a positive one. All right? So what happens? If a positron is emitted, a proton gets converted into a neutron. Okay? So, proton gets converted into a neutron and then a positron. So we're losing a proton here. As you can see here, this is carbon 11, but remember that carbon also has 6 protons. It converts into boron 11, and boron has 5. Why don't I write that down there? This is carbon 11, 6, and this is boron 11, 5. So you can see that the number of protons has gone down, but the number of neutrons, the atomic mass has stayed the same. So in order for this to happen, in order to lose a proton, but keep the number of the atomic mass, we have to have gained a neutron, and that's what happens. Okay? So the atomic number of the daughter nucleus is actually going to do what? If we convert a proton into a neutron, the atomic number is going to decrease. But as we just saw in that example, the mass number stays the same. Okay? As far as penetrating power compared to the others, it's relatively low. So, gamma has the greatest penetrating power. Beta emissions have stronger than alpha, and the positrons also are pretty low penetrating, and ionization power. Remember, ionization power is if a molecule or an atom gets hit by this thing, will it be able to pull an electron off of it? Okay? So, it's just the equations. Okay, so I've got phosphorus here, 3015. This is a 0, so this must be a 30 up here, because these two have to equal. And then 15. This is, just be careful of this. Some people are going to want to put 16 because of the beta electrons emissions, that we did earlier. But this is, remember, these two things have to add up to this. So this is 14, and that's going to be nitrogen. 14 plus 1 is 15. 30 plus 0 is 30. All right, same thing here. Oxygen 15. Oxygen 15 is radioactive. It gives off a positron, and in doing so, it also gets converted into nitrogen. So nitrogen no, that's not right. Sorry, that goes to 7. What did I do wrong there? 14 is not, 14 is, lost it there for a second. Sorry, that's silicon. My fault. I apologize. Silicon 14. This one is nitrogen. Nitrogen plus 1 is 8. 7 plus 1 is 8, and then we're going to keep the mass number. So this is silicon. Phosphorus gets converted into silicon. Oxygen gets converted into nitrogen. Okay? Now this clip here, I did not send you the notes, I don't think, but I can send you a blank one of them. But I do want to show this, even though it's only a minute and a half. So let's actually watch this during our video.
First to show that radioactivity could consist of 3 distinct types of radiation. The 3 types differ in their response to an electric field. A source of radioactivity is passed through a hole to form a beam. The beam is directed at a fluorescent screen, which is illuminated when it is struck. In the absence of an electric field, all the radioactivity beam strikes the target at a single point. When an electric field is applied, the initial beam is separated into 3 components. One of these is deflected upward by the electric field, indicating that it is negatively charged.
Now, we should have been able to predict this because we saw this early in the year. So when we have a magnetic polarization here going on. We've got a positive and a negative. You know that something that's negatively charged is going to veer toward that. This is what Thomson did when he discovered the electron. So this is going to get diverted closer to the positive charge. It's going to get pulled by this plate here. So it shows up on this phosphorescent screen being higher up. The one that goes straight through is not affected by the charge, and you could have guessed that as being the gamma, because gamma doesn't have a charge, it's just energy. And then you've got some particles that are getting diverted by the attractive pull of the negative side of this magnetic field. So, as you know, negative is going to attract positive. Now, the other thing that she will mention, but I want you to think about, is if this is straightforward, why is there so much of a gap here compared to here? This is no charge, this is negatively charged, that's positively charged. The positive charge is going to go for the negative, right? These are going to attract. So can you identify that particle number 1? It's an alpha particle. And why is the gap different between here and here? Well, if you remember about the masses of these things, beta particles are essentially electrons, and electrons really don't have much mass at all. Alpha particles, remember, are helium atoms, essentially, and the helium atoms have a mass of 4. So this is more massive. So this plate is not going to pull it nearly as much as that. That's why.
Radioactive emissions are called beta rays. A part of the beam is deflected downward, indicating that these particles are positively charged. These radioactive emissions are called alpha rays. Notice that the alpha particles are deflected less than the beta particles by the same electric field. This occurs because the alpha particles are more massive, but the amount of deflection is also determined by the relative energies of the different types of radiation. The portion of the original beam that is undeflected is due to radiation that is not charged. These emissions are referred to as gamma rays. Other experiments showed later that the beta rays are actually high-speed electrons. The alpha particles proved to be helium nuclei. The gamma rays are high-energy photons, analogous to X-rays.
Okay. That's that. So back to that. So these are emanating from a radioactive substance. Remember that Rutherford passed these through an electric field. The alpha particles have a positive charge. They were deflected toward the negative charge. The beta particles are negatively charged and opposites attract. I should put negatively, positively. And the gamma particles have no charge, therefore are not moved. Deflected is another word we could put there. Probably better with deflected. Okay, so be able to explain that. And lastly, nuclear equations. We've already done these, it's just putting them in the notes. So these are called transmutations. A transmutation is a change in the nucleus of an atom resulting in the change in the element. Okay? So this must result in a change in the atomic number. So this, a transmutation, is always going to result in a different element. So when we write equations, the atomic mass on the left side has got to equal the atomic mass on the right side. Okay? Likewise, the atomic number on the left side equals the atomic number on the right side. The addition of them, or subtraction of them. No, actually, just the addition. These two have to add up to what's over here. So here we've got thorium 90. Thorium 90. So this, they ask for an alpha decay. So alpha decay, again, is helium 4-2. So 90 minus 2 is 88. And 232 minus 4 is 228. Okay, and what's 88? 88, you should probably look. I don't have these memorized either, and these big ones here. So 88 is around uranium. It's not there yet. It's Ra, and Ra is radium. Okay, so that's a transmutation. Fill in the blanks of beta decay. How about a beta decay now? Now that 0 should be up there, but that's okay. So I've got magnesium, and then 12, -1, that's 11, and 24 and 0, so that's 24. 11, I do believe, is sodium. Sodium is 11, okay? So those are the nuclear equations. Oh, let's try one more. Fill in the blanks of positron. Positron, remember, you can show it as an electron with a +1. It could also be shown as a beta particle like that. Okay, so what does this have to be? The top is going to be 75. 75 plus 0 is 75. This is bromine. And 35, so this has to be a higher number. A lower number. See, I did it myself. 34 plus 1 is 35. So what is 34? 34 is selenium, Se. Okay? So be careful. I just did it myself. All right, tomorrow we'll learn about half-life. I already showed you what the homework is, and I'll post it. Have a good day.